Hello, fellow knowledge seekers. Welcome back to Cognition Chunks, your go-to channel for bite-sized pieces of knowledge. Today, we're embarking on an interstellar journey to our closest celestial neighbor, the Moon. So, strap in, and let's blast off into the cosmos. Our adventure begins with a peculiar substance known as KREP. Despite its eerie name, KREP isn't something out of a horror movie. It's a type of lunar rock that's rich in potassium, K, rare earth elements, REE, and phosphorus, P. These elements are not just random letters from the periodic table, they hold the key to understanding the Moon's geological history and interior. You might be wondering, what's so special about these moon rocks? Well, these aren't your average pebbles. KREP rocks are like the Moon's autobiography, giving us valuable insights into its past and present. They're the lunar equivalent of a time capsule, preserving billions of years of lunar history. According to a study by M. Wieczorek and R. J. Phillips, the Procellarum KREP terrain, a unique geochemical province on the Moon, is where most of the Moon's heat-producing elements are located. It's like the Moon's nuclear reactor, generating heat from the decay of radioactive elements. This region is crucial to understanding the Moon's thermal history and the evolution of its crust. But the story doesn't end there. The thermal evolution of this region, modeled by these researchers, suggests that partial melting of the underlying mantle is an inevitable outcome due to the high abundance of heat-producing elements. It's like the Moon's version of a hot fudge sundae, but instead of delicious molten chocolate, we have molten rock, or magma. In another study by C. K. Shearer and J. J. Popike, they delve into the magmatic evolution of the Moon. They've identified different stages of lunar magmatism, and guess what? Our friend KREP plays a starring role in this geological drama. It's like the Moon's very own reality TV show, Keeping Up with the KREPians, where KREP rocks are the main characters influencing the plot of lunar evolution. Finally, a study by F. M. McCubbin and colleagues found that lunar apatite, a mineral found in KREP rocks, contains varying concentrations of fluorine, chlorine, and a missing structural component attributed to OH. This finding is like a plot twist in our lunar saga, suggesting that the Moon has a heterogeneous distribution of volatiles within its interior. It's like the Moon's secret recipe, with a pinch of this and a dash of that, creating a complex and diverse lunar interior. So, there you have it, folks. KREP rocks aren't just cool because of their name, but they also tell us a lot about the Moon's interior and its geological history. They're like the Moon's diary, filled with stories of its past and clues about its present. Who knew rocks could be so fascinating, right? The Procellarum KREP terrain, Implications for Mare Volcanism and Lunar Evolution, is a study by M. Wieczorek and R. J. Phillips, published in 2000. The paper focuses on a unique geochemical crustal province on the Moon, known as the Procellarum KREP terrain. The authors used geophysical, remote sensing, and sample data to demonstrate that the Procellarum and Imbrium regions of the Moon make up this unique province. They found that a large portion of the lunar crust in this area is composed of material similar in composition to Apollo 15 basalt. This basalt has about 300 times more uranium and thorium than chondrites, suggesting that the Moon's heat-producing elements are located within this single province. The spatial distribution of mare volcanism closely parallels the confines of the KREP terrain, suggesting a causal relationship between the two phenomena. The authors modeled the thermal evolution of this region using a simple conduction model. They showed that as a result of the high abundance of heat-producing elements found in the terrain, partial melting of the underlying mantle is an inevitable outcome. Specifically, by placing a 10 km layer of KREP at the base of the crust in this area, their model predicts that mare volcanism should span most of lunar history and that the depth of melting should increase with time to a maximum of 600 km. The 500 km seismic discontinuity observed on the Moon may represent this depth of melting. Their model also predicts that the mantle should remain partially molten for a few billion years. Thus, the Imbrium impact event likely excavated into a pre-existing magma chamber. The authors postulate that KREP basalts are a byproduct of the mixing of URKREP with shallow melts from the mantle. Since Mg-sweet rocks are derived from crystallizing basalt, the provenance of these plutonic rocks could also be from the KREP region of the Moon. Magmatic Evolution of the Moon is a study by C. K. Shearer and J. J. Popike, published in 1999. The paper provides a comprehensive review of the history of lunar magmatism, which has been reconstructed by numerous researchers over the past 3 decades. The authors grouped the history of lunar magmatism into multiple stages of activity based on the rock types sampled by the Apollo and Luna missions. They evaluate models for each stage, providing insights into the magmatic evolution of the Moon. Here are the stages they discuss. 1. Stage I is the differentiation and associated magmatism. Partial melting of the Moon soon after accretion was responsible for producing an anorthositic crust and a differentiated interior. The extent of this processing depends strongly on the mechanisms that induced the melting. 2. Stage II is the disruption of magma ocean cumulates. Soon after most of the magma ocean crystallized, the cumulate pile experienced gravitational overturn, resulting in the transport of late-forming cumulates deep into the mantle and mixing on a variety of scales. 3. Stage III is the post-magma ocean highland magmatism. The Faroan anorthosite suite was probably produced during this stage, and the slightly younger Mg suite and alkali suite plutonic rocks may have been generated by decompressional melting during the gravitational overturn. A KREEP signature was incorporated into these primitive basaltic magmas through assimilation near the base of the crust or through hybridization with the mantle. 4. Stage IV is the pre-basin mare volcanism. Sample analysis and remote sensing data indicate that mare volcanism, KREP basalts and high alumina basalts, occurred contemporaneously with periods of highlands plutonism on the lunar surface. The relationship between these contemporaneous magmatic activities is not clear. 5. Stage V is the late basin remelting and eruption of mare basalts. Basin-associated mare volcanism followed the late heavy bombardment, possibly as an extension of the thermal event that initiated the mare volcanism. The authors conclude that the magmatic evolution of the Moon was influenced by early differentiation and catastrophic bombardment on mantle dynamics, magmatism, and eruptive style. They also discuss the role of KREP in the magmatic evolution of the Moon. Fluorine and chlorine abundances in lunar apatite, implications for heterogeneous distributions of magmatic volatiles in the lunar interior, is a study by F. M. McCubbin and colleagues, published in 2011. The paper discusses the composition of lunar apatite, a mineral found in KREP rocks, and its implications for the distribution of magmatic volatiles within the Moon's interior. The authors analyzed apatite from mare basalts, the magnesian suite, alkali suite, and KREP-rich impact melt rocks using an electron probe microanalysis routine developed specifically for apatite. They found that all lunar apatite grains are predominantly fluorine-rich, but they also contain varying concentrations of chlorine and a missing structural component that they attribute to OH. The authors found that the apatite in mare basalts is compositionally distinct from the apatite in KREP rocks, which had similar compositions. The mare basalts are depleted in chlorine, and many have a stoichiometry that suggests significant OH, i.e., greater than 0.08 formula units, whereas the magnesian suite, alkali suite, and KREP impact melts are enriched in chlorine and do not typically have a stoichiometry that could be attributed to OH, within the detection limit of 0.08 SFU. From these data, the authors infer that the residual liquids from which the mare basalts crystallized were enriched in H2O relative to F and Cl at the time of apatite crystallization, whereas the residual liquids from which the KREEP rocks crystallized were not. The volatile abundance in the mare basalts is identical to that previously observed in picritic glasses. This result indicates that the observed volatile signature in the glass source is the same as that in the basalt source regions. The authors conclude that the Moon has a heterogeneous distribution of volatiles within its interior, with a chemical divide, with respect to volatiles, existing between magmas that arise from partial melting of the mantle and those seen in regions of the Moon with contamination by the KREP component. The Moon is a sort of time capsule, its rocks and surface preserving a record of the early solar system that has remained relatively unchanged for billions of years. There are several ways studying lunar rock composition can reveal information about the early solar system. Preserving the early solar system's history *. Unlike Earth, the Moon doesn't have plate tectonics, weather, or life, which on Earth lead to erosion, the formation of sedimentary rocks, and other processes that over time alter or destroy geological evidence. Thus, lunar rocks preserve a much more intact record of the early solar system. By studying these rocks, scientists can gain insight into the conditions that existed in the solar system's early years. Age-dating * lunar rocks, particularly those brought back by the Apollo missions, are some of the oldest rocks we have access to. By dating these rocks, scientists can establish a timeline for major events in the early solar system. For example, dating of lunar rocks has provided evidence for a proposed period of intense meteoritic bombardment in the solar system approximately 3.9 billion years ago, called the Late Heavy Bombardment. Information about the Moon's formation * The prevailing theory about the Moon's formation is that a Mars-sized body collided with the early Earth, and the Moon formed from the debris of this impact. The specific composition and isotopic signatures of lunar rocks, particularly the similarities and differences compared to Earth rocks, provide key evidence supporting this theory. Presence of water * Recent studies have found traces of water in lunar rocks, which could suggest that water in the inner solar system was more abundant in its early history than previously thought. This discovery has implications not only for the history of the Moon and Earth but also for our understanding of the early conditions that led to the formation of habitable planets. Traces of the solar wind * The solar wind, a stream of charged particles emanating from the Sun, implants ions into the surfaces of objects throughout the solar system. Some lunar rocks contain these implanted ions, which can provide information about the history of the solar wind and the early Sun's activity. In summary, lunar rocks offer a wealth of information about the early solar system, from its age to its composition, even the history of the Sun. As scientists continue to study these rocks with increasingly sophisticated tools, our understanding of the early solar system continues to evolve. That's all for today's episode of Cognition Chunks. If you enjoyed this lunar adventure, don't forget to hit that like button and subscribe for more knowledge-filled journeys. Remember, the universe is filled with wonders waiting to be discovered, so stay curious, stay nerdy, and keep chunking. Until next time, this is Cognition Chunks, signing off.